let's talk about prime ideals. So I've written the definition here. Let R be a commutative ring with 1. A proper ideal P in R is called a prime ideal if AB in P implies A is in P or B is in P. So that's the key condition, and this has to hold for all AB in R. So to parse this definition, so these are the most important kind of ideals, and they generalize. We'll see the notion of prime numbers in Z and the notion of irreducible polynomials in one variable polynomial ring over a field. To parse this definition, I want to first talk about this notion of divisibility among prime ideals. So we're going to give some definition that would make this condition look more like the condition that you have for a number being a prime number. So let R still be a commutative ring with 1 and take AB in R. So remember, what does it mean to say that? Recall that we say A divides B in R. This is the notion for divides. So this vertical bar means divides. If there exists some C in R such that B is AC. So B is a multiple of A. So for example, 3 divides 15 in Z, right? Because 15 is 3 times another integer. 4 does not divide 15 in Z because 15 is not 4 times another integer. However, 4 does divide 15 in Q because 15 is 4 times another rational number, etc. Yeah, so this is the notion of divisibility between two elements. We want to rephrase this in terms of ideals. So verify, this is a little exercise, that the following are equivalent. 3 statements. The first, A divides B. What does that mean? We just said it. It means that B is A times another element of the ring. That means B is a multiple of A. The set of all multiples of A form what is called the principal ideal generated by A and denoted by parenthesis A. So saying that A divides B is exactly saying that B is in this principal ideal. But then, furthermore, if B is in this ideal, then any multiple of B is also in this ideal. So all multiples of B form the principal ideal generated by B. So all those guys are in the ideal generated by A, because any multiple of B is also a multiple of A, because B itself is a multiple of A, which means that this ideal is a subset of that ideal. So the ideal generated by B is a subset of the ideal generated by A. And now we have rephrased this notion of divisibility of elements in terms of divisibility of ideals, or rather containment between two ideals. And the right hand side makes sense for any two ideals. So we make this thing the definition of divisibility among two ideals. So this discussion that we just had motivates the following definition. Let I and J be two ideals in R. Say that I divides J if, you guessed it, J is a subset of I. So according to this definition, you see, multiples of 15 is a subset of multiples of 3, because any multiple of 15 is also a multiple of 3, or if you prefer in this notation. So this is just saying that the ideal of 3 divides the ideal of 15. So that's the point of this definition, that it generalizes divisibility of numbers exactly. or rather divisibility of elements, exactly. So we do have 3 divides 15 in terms of ideals also. Okay, and I meant one more definition. If you have an element and an ideal, let I be an ideal and B be an element, we say I divides B, the element B, if it divides the ideal generated by B. And this is a transition that you have to get used to. Whenever we apply these ideal notions to element, it really means it applies to the principal ideal. And now you verify. Again, 3 simple statements are equivalent. Saying that I divides, an ideal divides an element is same as saying that the ideal I divides the principal ideal generated by B, which just means that the principal ideal generated by B is a subset of I. So these 2 statements are equivalent. But then the ideal of B is a subset of I if and only if B is in I. Well, that's very straightforward. So these 3 statements are equivalent. And now you see that the 3 statements here are exactly generalizing the 3 statements up here. From an element, we have promoted the statements to the case of ideals. Instead of an element A, here we have an ideal I. So this is a rather good generalization, all this shows. And in terms of this new notion of divisibility among ideals, what does our definition of prime ideal say? This translates into saying A in P is same as saying P is in dividing A. And this B divides P is same as saying P divides B. And similarly, AB in P is same as saying P divides AB. So what the statement is saying is that if P divides AB, then P divides A or P divides B, which, as you recognize, is the condition for a number being a prime number. But now we're not, capital P is not a prime number, it's some ideal in some commutative ring with 1. And divisibility means this notion that we just defined on the right hand side here. But in terms of that generalization, the condition of being a prime ideal is exactly the same as the condition that we had before for a prime number. Okay. So we'll give examples in a little bit, but first we have this recognition lemma, how to recognize a prime ideal. And it's just like the lemma we had for maximal ideals. So recall, we had the lemma that a proper ideal in a commutative ring with 1 is maximal if and only if R mod M is a field. Now we have a similar result. A proper ideal is a prime ideal if and only if R mod P is a domain. And the proof of this is rather straightforward. You just translate this condition. You see, we have this surjective ring homomorphism. So you have to relate something in R with something in R mod P, and this surjective ring homomorphism from R to R mod P called the quotient homomorphism. What does it do? It takes an element to the corresponding coset. Let's write A bar instead of that. Also recall, pi A, pi B is pi of AB, meaning AB bar is same as A bar, B bar. And the coset of an element is the trivial coset, the coset of the 0 element, if and only if A is in P. I want you to recall these 2 statements. Now given this, let's translate the phrase up here. the phrase up here. AB in P. In P implies, or let's say if AB in P, then A in P or B in P. How does that translate? Saying that A is in P is same as saying A bar is 0 in R mod P. And saying that B is in P is same as saying B bar is 0 in R mod P. And saying that AB is in P is same as saying that AB bar is 0 in R mod P. But AB bar, you see, is same as A bar, B bar. So this sentence here translates to saying that if AB bar is 0, then either A bar is 0 or B bar is 0. And that's exactly saying that R mod P is a domain. Domain means when a product of two things is 0, then one of them is 0. And that's roughly the idea of the proof. Once you have this lemma, you have an immediate corollary that every maximal ideal is prime. So you have seen example of some maximal ideals, so those are certainly prime ideals. Why? Because if you have a maximal ideal M, then R mod M is a field. A field is certainly a domain, so R mod M is also a domain. And if it's a domain, that means it's a prime. Okay? So that's why this is true. So how about examples quickly? In Z, the prime ideals are the ones generated by prime numbers. And because these are all maximal ideals after all, and also the ideal generated by 0. You see, because quotienting by the 0 ideal just gives you back the ring itself, Z itself, and Z is a domain. Or in other words, if we just go by the definition, saying that a product of two things is in this ideal is just saying AB is 0. But because Z is a domain, a product of two things being 0 means one of them is 0. Okay. In one variable polynomial ring over a field, the maximal ideals are again the prime ideals, I'm sorry. The ideal generated by 0 and the ideals, this will be proved in a bit, generated by irreducible polynomials F. So there is no new examples. These are all maximal ideals. So to get some new examples, you have to go to the two variable polynomial ring. Well, 0 is a prime that is not maximal, I suppose. That is a new example. But if you go to two variable polynomial ring, recall we proved last time that fxy mod x is fy, which is a domain. So this is a prime ideal. But it's not a maximal ideal, we saw. There is a bigger one. But this is not maximal. And maybe we'll have some more examples in the exercises. And there's a lot more to say. Maybe we'll talk a little bit about primes and maximal ideals in PID.